Now it's taken. So the probability that xn is equal to 0, this guy is equal to 0, is the probability that u is larger than 1 over n. And that's just 1 minus 1 over n. And the probability that xn is equal to n is the probability that u is less than 1 over n, which is 1 over n. So this goes to 1, this goes to 0, and clearly xn will go to 0 in I won't go into the details, but it goes to 0 basically in one of the most natural possible ways. It means that it goes to 0 in probability, and it also goes to 0 almost surely. So this sequence really converges to 0, but there's one problem. It's that this sequence has a finite mean. The mean is just going to be n times the probability that it's equal to 1 to n. So it's n times 1 over n plus 0 times 1 minus 1 over n, which is just equal to 1. So the mean is finite. It's equal to 1 for all n. Expectation of xn squared is n squared times 1 over n plus 0 squared times 1 minus 1 over n, which is equal to n, which is finite for all n. But expectation of xn, which is equal to 1, does not converge to expectation of the limit. So the limit of the, so xn is here, xn is here, the limit of the xn's is 0, and we don't have convergence of we cannot exchange limits and expectations. So it means you have to be careful when you're playing around with limits and expectations, because even in certain simple cases like this one, this is a very simple case, everything is nice, everything is finite, there's no pathology, you cannot exchange limits and integrals. And the problem, I don't see if you see where the problem with this sequence is, that we don't have in this course. Does somebody see what the problem with this sequence xn is? Or with its variance? Probably not. As n grows, the variance explodes. So we don't have convergence in L2. So we're not in a nice space. It's not a nice random variable. It's not a nice sequence. So this here is annoying. So there's the three magical results that all of you need to at least have heard of are, well, they are due to a French mathematician, a French guy called Henri Lebesgue. I'd say he was in his 20s when he did this. So it's published when he was 30, but I'd say he invented all this when he was in his 30s. So he basically invented integration, or at least he invented a new version of integration. He invented the theory of measure theory, and he proved, well, these results: dominated convergence theorem, wait, first of all I need to define things. So, definition. If you have xn, a sequence of random variables, if you have x a random variable, we say that xn converges to x almost surely if the probability that xn converges to x is 1, we say that xn converges to, sorry, and here we write so we write xn converges almost surely to x. We say that xn converges in probability if for all epsilon larger than 0 the probability that xn minus x is larger than epsilon goes to 0. I have too many probability here. So in probability, almost surely, we write this, and we say that xn converges to x in L2. We've already seen this, so I'll just put it in parentheses. Xn converges to x in L2 if expectation of xn minus x squared goes to 0. And we write this. Now, with this in hand, we have various notions of limits of random variables, and we have, of course, we still want to know when we can exchange limits and expectations, and we have three major results, which are, first of all, the dominated convergence theorem, which says what? Well, it says that if you have a sequence such that xn is smaller than y, so the absolute value of xn is smaller than some y with y which has a finite mean, then xn converges. Then, if xn converges to some x almost surely, it follows that expectation of xn converges to expectation of x. That is, we can exchange limits and integrals. Second theorem that is very useful is the monotone convergence theorem. So I won't be using it very often, but I might be using it sometimes, and I'll call it the DCT. The monotone convergence theorem says that if xn is a sequence of random variables which are positive and increasing, then if xn converges almost surely to some x, necessarily the convergence happens also in the means. And the third result you need to know is Fatou's lemma, which says what? It says that if you have xn larger than 0 a sequence, then the expectation of the limit inferior is less than the limit inferior of the expectations. So what we've done here is this little reminder. Well, you should keep it safely stored somewhere. I'm not going to type it up, so I'll let you. Well, either you rewrite it or you just print out this, but it's something that you need to know about the possibility of exchanging. So about the notions of convergence, that there are many notions of convergence. Here we focus on basically 3, almost sure, in probability, and mainly in L2. And then we have these, well, mainly 2 results: dominated convergence, monotone convergence, and also this one, which would allow us to exchange limits and expectations. If you were with me in a room, I would ask you if you've seen this already. Here it's a bit complicated. Well, you can raise your hands, so could you, if you're still awake and listening to me, could you raise your hands for those of you who have seen this material? Yeah, that's more or less what I was expecting. So 3-4 people have seen this. The rest of you, well, don't worry too much. Again, it's a bit like the material in chapter 2. So I try to skip over some details to make the course not too intricate mathematically, but still, I mean, you need to have this kind of knowledge somewhere in your background. So you have to know that this is not always possible. You cannot always exchange expectations and limits. Try to understand this example. If you don't understand it well, I can explain it to you again slowly, and you'll see that it's actually quite a healthy example showing that things are not easy, because you can construct counterexamples which will make things break down. So here's an example where you can't exchange limit and integrals, and then we have these 3 magical theorems which tell us what we can do in general. You can't do better than this. And those of you who've done maths, so seemingly Orphée, Ferdinand, and Céline, I don't think I saw other names. Well, then you've studied this kind of stuff and you know how you can play with that. But for the others, don't worry too much. I just want to be able to refer to it. And so now we can go back into the slides and start moving a bit faster. Where is it?
Sorry.
Yes.
Just for the last one, Fatou's lemma.
Yeah.
How can we interpret this limit inferior? Is it also an almost sure limit, or?
Yeah. So this it's you're perfectly right to ask the question, and I was trying to skip over it, hoping that you wouldn't ask. So, do you know what the limit inferior is, Clara?
I was told it was like the smallest when you take overall subsequences.
Yeah. So, yeah, it's good. I mean, you're perfectly right. All the rest of you, you're very lucky to have Clara to correct, to catch me up on this. So I make a small another aside inside the aside. So aside in the aside. So we're like an inception here. We're inside a dream, inside a dream, inside a dream. So if I look at sequences of numbers xn, which are real numbers, then I'm not allowed to write this. Limit of xn does not exist in general. The simplest example that you can think of is xn is minus 1 to the power n. Well, that's what? That's 1 minus 1, 1 minus 1. It does not converge. As n grows, this goes nowhere. So it does not have a limit. So when I write limit of xn for this guy, it makes no sense. So if now you have a sequence of random variables, let's take them real random variables to simplify, well then limit of xn is not even a random variable. It's not well defined. So in fact, when I'm writing, so in fact I can't even write this guy. I mean, this literally makes no sense in general. Unless I know that these guys converge, I cannot write this. So it doesn't make sense. So how do we get around this? Well, there's two very important concepts in analysis. So the limit inferior of a sequence is the limit as n goes to infinity of the infimum over all xk's for k larger than n. So it's the limit of the tails of the sequence. This is the tail of the sequence. And you look at the limit of the tails of the sequence, and yeah, small exercise for those of you who like this kind of stuff. We can talk it over, but outside the class time. This limit always exists. Always exists. And to make a long story short, it's actually easy to see because this is. Sorry, I have to be a bit more careful. It always exists, but it could be infinite. It could be equal to minus infinity, but it exists. It does make sense as a number, whereas this limit here does not exist. And why is it the case? Well, this sequence of infimums is going to be an increasing sequence, and any increasing sequence is necessarily convergent. Yes, Evo. I'm probably going to ask her next year. The other way around, if we look at the limit superior, then it's this thing here. Again, you look at the limit of the suprema. Again, you're looking at the tail of the sequence. No, that's not correct. This is correct. This is the tail of the sequence. And we have this here, like that. And again, same thing here. This, well, maybe I can erase this and simply copy. Exercise. This limit always exists, but it could be plus infinity. And as a consequence, if you have xn, a sequence of random variables, this limit inferior and limit superior always exist. So they are well-defined random variables. And we know also that xn will converge almost surely if and only if, is that an exercise? I think it is an exercise that you could do also if you're interested in this kind of stuff. If and only if the limit inferior xn is equal to the limit superior of the xn. And that's why if you want to mention an expectation of a limit of a sequence, well, in general, if you don't want to impose convergence, so here we impose convergence to deduce something. Here we impose convergence to deduce something. If you don't want to impose convergence, well, you can't write the limit. You have to write either limit sup or limit inf. And if you take limit inf, well, then this is a well-defined random variable. It has an expectation, which could be minus infinity. And what we know is that this expectation here is always smaller than the limit inferior of this real sequence. And this is, again, a number which exists. Okay? Does that answer your question, Clara?
Yes, thanks.
So, yeah, all this is stuff that should be in basic maths curricula. You've probably all forgotten this. I mean, I remember that I didn't like limit inferiors when I was in my studies. Okay, so with all this we can go back to the slides. God, I'm slow. And I will go a bit faster now. I'm going to leave a few things not done, and these things not done will be left for you to do unless I tell you that they're not for you to do. So let's go back here. So this is stuff we already discussed last week. I'll just go over it quickly again. Hopefully you'll understand it better now that I've given more explanations. So we have seen that under certain circumstances on the parameters phi1 you had existence of stationary and solutions or causal solutions and so on. And now we would want to write clear conditions on the parameters of your ARMA model for which you know that you have existence of stationary, causal, and a concept that I haven't talked about yet, invertible solutions to the equation. And now it's not hard, as I said last week, it's not hard to see that, I mean, the only thing that's going to matter here is, so the ZT are white noise, which means 0 and variance sigma squared. This sigma squared basically plays no role for the moment in our problem because it's it would always simplify. Well, it's not intrinsically, it does not affect the behavior of the process. So the only things that matter are the parameters of your AR and MA polynomials. And now we go back to what we said in section 2. So we'll we look at in general we'll be looking at processes defined in terms of processes and linearly defined in terms of processes with certain coefficients. And we want to understand what happens in general with these guys. So if I go back to chapter 2, what did we say in chapter 2? If I find it, chapter 2, page chapter 2, page 8. We saw that if we had this, then we had that this thing converges in L2 if and only if the sum of the coefficients squared is finite. So that's what we saw in chapter 2, page 8. Now we're going to work in more generality and take a linear combination of xt's with certain coefficients, not necessarily all positive. So the first theorem, maybe I'll go over it again. It just tells you how to deal with this structure here. So we have a random process, any random process. We have real numbers which are absolutely summable. Again, I insist, this is a stronger condition than the sum of the squares being finite. So this is stronger than this. It's very easy to determine a sequence which satisfies this but does not satisfy this. Think of the 1 over j's. We take a sequence like this. We consider this this polynomial, and what will happen is that if this sequence is uniformly bounded, then this series here, it's stronger than L2 convergence. It's absolutely convergent with probability 1. So the probability that this guy here converges is 1. And if we have more than this, so if we have the fact that maybe I should put this here. So the expectation of the square is finite. Then this same series will also converge in L2. I'm not going to go over the proof again, but I would like you to read it and understand it and ask me questions if there are problems with the understanding of this proof. It follows as a consequence of monotone convergence theorem on the one side and Fatou's lemma on the other side. Okay. So what does it mean in practice? Well, for the AR1 process, we can go back over what we said and say it more efficiently, because if we have a process like this, well, it's been rewritten like this. So that's what. So if I'm in example 3.14, we have just seen what? We have just seen that the solution to our equation was this. So this is what? Well, if I go back into the notations here, it's so the psi j's are 0 for, psi j's are going to be 0 for j less than 0, and phi 1 to the power j for j larger or equal to 0. So that's the psi j's. The xt's, so be careful here of the notations. We're looking at linear combinations of the xt's, so here we're looking at linear combinations of these guys. So what's playing the role of an xt in this theorem is actually the zt's here, and what we need is that we need the supremum of the expectations of the zt's to be finite, which is stronger condition than what we have. So if we have this condition, what am I? Just quick check. Yeah, it's a stronger condition. No, it's a weaker condition. Yeah, sorry, I'm talking rubbish. Zt here, if I take a square, this is less than this. Yeah, sorry, I was talking rubbish. This is a weaker condition. So because we know that this guy here is 1, we know that this guy here is less than 1 for all t. So that we know this, because it's actually less than 1. This is equal to 1. Well, it's not equal to 1, it's equal to sigma squared, like that. And therefore we can apply the proposition. No, we also have to check. We have to check what? We have to check that we have this condition of absolute convergence of the coefficients. But that's also easy, because the sum of the coefficients is just the sum of the phi 1 to the power j with an absolute value here, and j going from 0 to infinity. And that's an easy result, because that's 1 over 1 minus absolute value of phi 1, which is also finite. So now we can apply proposition 3.13, and we can say that this sequence here, this series is absolutely convergent with probability 1. And we can also, but we already knew it, we can also say that xt converges also in L2. So applying this proposition 3.13 just allows us to confirm things that we already knew, and so we get the conclusions that are here. Okay? You're still there? You seem to be still there. Okay. More generally, if we read proposition 3.13 a bit better, again, this is not proof with a star, it's an exercise for you to do. You can see that the sequence here converges in L2 if and only if the sum of the coefficients squared is finite. That's something we already saw. It's simply a proposition. Where is it? Well, it's a proposition from chapter 2. So we saw this in chapter 2, and now we have a different proof of the same result. And we know that if, moreover, the sequence here is such that it converges absolutely, and then this will also converge almost surely, and in L2, and both limits are will coincide. And yeah, maybe I said I would dispense you with the proof of this result, but that's a bit stupid because it's a really important result. So I changed my mind. I don't dispense you with the proof of this result. Now consider a general linear sequence of this form. So linear coefficients and some sequence which is stationary, and that's the only assumption we make. Then we can simply get the covariance structure and read the covariance structure by directly. So we can read the covariance structure of any linear process defined in terms of zt in terms of the covariance of the zt's and the coefficients in your expansion in your combination. And how do you do that? Well, if we do it savagely, so proposition 3.16, if xt is a combination of psi j z t minus g, then if I'm not checking the limits of the expectations, so if I'm not being careful, I can write this. So I exchange, so it's here that I have to be, this is the dangerous step. It's when I'm exchanging the sum and the expectations. If my process zt is stationary, it has a mean which does not depend on the time, so we're left with this. Secondly, if I look at the covariance of xt plus h, I will have the covariance of this guy with the same guy, except that it's t plus h minus j. Maybe I'll put a k here so I don't get my indexes mixed up. And then again, I have to be careful if I can exchange or not my summations. So I do this. And here I use stationarity of my zt's to say that this is equal to gamma of the difference between this guy and this guy. So it's gamma of h minus k plus j. And what's remarkable in this theorem is that in order to be able to do this step and this step, well, all you need to know is you need to be able to exchange expectations and limits, and for this all you need is to have the convergence in L2, and this is guaranteed. This is guaranteed by that condition here. So we're actually very happy because with this we recover results that we already had, but with different arguments. So we recovered the covariance of a moving average, and we recovered the covariance structure of an autoregressive of order 1. Okay. And now let's move a bit faster. So a very important theorem in the theory of ARMA processes is the following. It says that, well, in fact, it's quite easy. I mean, the proof is not easy, but it's quite easy to see when such an equation here has a unique stationary and causal solution. And the condition is very easy. It's that if these two polynomials have no common roots, so there is no root which, so there is no z which cancels this and this at the same time, then you have a unique stationary and causal solution if and only if there is no z between -1 and 1 which cancels this guy. So if all the roots of this polynomial here are outside of the unit disk, so maybe I write this. So this condition here, it says that all roots are outside of the unit disk in the complex plane. Well, then your equation here will have a unique stationary and causal solution. So it's actually very, very easy. If I give you an explicit polynomial ARMA process, it's very easy to determine whether or not you will have an existence of a unique stationary and causal solution. Moreover, the theorem here gives you the solution. The solution is given by, well, it's given formally, it's given by something extremely, exquisitely simple. You take the polynomial here, divide it here, and you get the solution. I know I've already said this, but it's remarkable, but it's also remarkably false if you try to do it, at least without being careful, because obviously you can't divide by this is a differential operator, well, a difference operator. You cannot divide by a difference operator. This makes no sense. But visually, formally, it's quite easy. You just take this and divide. And what we mean by this here, so this I will call it psi of b. And what we mean by this is that, well, your polynomial here, theta, well, sorry, your ratio of polynomials will have a series expansion. Your ratio of polynomials here will have a series expansion. It will be an analytic function which converges. And this series expansion gives you the coefficients of the linear expression of x in terms of z. So what do I mean by this series expansion? I just did an example last night, so maybe a small explanation. So theorem 3.20, I considered the case phi of z is equal to 1 minus 0.05 z minus 0.6 sorry, minus 0.6 z squared. I take theta of z, which is 1. Well, then the roots of theta, well, there are none, because this polynomial is never 0. But anyway, theta doesn't matter. The roots of phi, well, I mean, it's not hard to solve this. When is this equal to 0? You should all know this formula, but I wouldn't do it by hand. It's not worth it. Use R or use Mathematica to see that the roots of this guy are z1. So you have two roots. It's minus 4/3, and z2 is plus 5/4. So I didn't check, but I suppose that if you plug this in here and this in here, you get 0. And these roots are both outside of the unit circle. So the theorem applies. The theorem applies. You have no common roots between this guy and this guy. Both roots are outside of 1. So there exists unique stationary. There exists a unique stationary and causal solution given by what? Well, given by xt is psi of b times zt, where psi of z is the series expansion of this guy, so 1 divided by this guy, so this. Now, I don't know if you all remember what a series expansion is, but you again recall. You know, I mean, you cannot not know what this is. So recall Taylor's theorem, for example, which says that f of x is. So I'm going to take the Maclaurin version. F of x is equal to the sum under certain conditions, which I won't detail. F of x is equal to, for all n, you can write it like this. Does this remind you of things? This Maclaurin expansion? I guess the math students, yes. The others? No? You're all asleep?
Yes.
Okay, so I have one yes. Yeah, Ferdinand, that's... if you don't remember that, that would be... So Ivo, it's I mean, without joking, most of modern mathematics is Fubini and Taylor's theorem. Statistics is an application of Fubini and Taylor's theorem. So the idea is that you can always approximate any function by a polynomial, and the coefficients are given by the derivatives of your function of order k divided by k factorial. So we won't really be needing this in the sequel, so you can maybe look it up on Wikipedia. R and Mathematica, for example, do this automatically. You just ask. So I did in Mathematica, I asked for the expansion here, and I got this expansion here automatically from my software. Where, so what did I get? I got 1 plus 0.05 z plus 0.6025 z squared plus 0.060125 z cubed, and you can go on up to whatever order you want. So I stopped at order 10. And so this will be psi 1. This will be psi 2. This will be psi 3. This will be psi 10, and so on, and so on, and so on. Therefore, well, we get our from the theorem we get the representation, and from these psi's, if we apply proposition, I forget which number, we also get the covariance. So it's actually Roland, yes, it's mat 01 exactly. It's the basics of the basics. Here, don't worry. I mean, we won't be using it either. You won't be doing this by hand, and it's so if you're using R, it's all pre-encoded in R. So it's all perfectly automatic. I think I forgot about my kids. I'm just going to check if they have arrived. Sorry. I'll be right back. I'm not going to leave the Teams, but I'm just suddenly worried because my kids should have been there half an hour ago, and I can't hear them, which is never good. They're not there. Okay, I'll be right back. I'm suddenly worried. I'll be right back. Okay, sorry. Found them. They're still alive, which is good. Well, at least 3 out of the 4 are still alive. There's one missing, but I'm not so worried. Still there? Okay,
Yes.
at least I felt the noise there. Okay, so this is quite powerful because I mean, from this theorem, in principle, everything is solved. Now, I don't do the proof because the proof is actually, I mean, it's actually too hard for. I mean, it's not hard for the math students. So if the math students or people, if you are interested in this kind of stuff, please go and see, for example, in theorem 2.1 of Neusser, he does the proof in quite some detail. Although the proof relies on other results, so and it's not worth spending a lot of time on this here. But the idea is you just try and see. I mean, the secret of the proof lies in the way you do this expansion here, and depending on the properties of this expansion, we will have nice behavior, and the properties of this expansion depend only on the roots of the denominator here. And what's remarkable is that if the roots are sufficiently far from zero, so that means that they have to be at least outside the unit disk, then everything is easy. So that's quite a remarkable achievement. Now, with this in hand, we can make a few remarks. First remark is that this remark here is useless, so you can simply bar it off. I should not have left it in here, so this is redundant. Second remark is that if your polynomial has zeros inside and outside the unit disk, but if you have no zeros on the unit circle, then in fact there will exist a unique stationary solution of this form, but this solution will not be causal. It will have dependence on the future. Secondly, maybe this one is better. If the polynomials here have no common root, but the denominator polynomial does cancel out for some z on the unit disk, on the unit circle, sorry, then there exists no stationary solution. There exists no stationary solution, and that means that I mean that basically that's what we already saw. We had seen that in the AR1 case. We had seen that in the AR1 case. Sorry, it's AR1. We saw that if phi1 was less than 1, then you had a unique stationary stationary solution, and it was causal. If phi1 was equal to 1, then there was no stationary solution. No stationary. I'll do this better. Sorry, I'm not being careful. I'll do this better. Here. So, still intuition on this theorem. So, on theorem 3.20, so in the AR1 case we had xt is equal to phi1 xt minus 1 plus zt. So the polynomial phi of z was 1 minus phi1 z. Theta of z was just 1. There are no common roots. And we saw what? We saw that there were three cases. First case was phi1 is less than 1, then there exists stationary and causal solution. Secondly, we saw that if phi1 was equal to 1, then there was no stationary solution. And thirdly, we saw that if phi1 was larger than 1, then there exists a stationary solution, but not causal. Now this will obviously recover, this will obviously be implied by the theorem here. And how do we see that? Well, there are no common roots, but so the roots of theta and theta, there are none. So it's the empty set. And the roots of this guy are what? So what is the root of this polynomial? It's the value of z for which this is equal to 0. And the value of z for which this is equal to 0 is what? Well, it's 1 over phi 1. So what do we need? We need that if we look at the theorem, we need that the roots of this guy be outside the unit circle. That means that we need the roots to be larger than 1, which is equivalent to phi 1 less than 1. Is that okay for everybody? Guess it is. Okay, so the condition that we had already seen in this case is in fact implied by this theorem here. Same thing here. If phi 1 is equal to 1, then we have a root on the unit circle in dimension 1. And if phi 1 is larger than 1, then we have a solution which is inside the unit circle. Therefore, we are not in the circumstances of this theorem here. Okay? Okay. Let's move on. The third remark, so this one is covered. This one is covered, and now this one. If your polynomials have a common root, then there are two possibilities. If no common roots lie on the unit circle, then there exists a unique stationary solution which can be obtained simply by cancelling the common factors of the polynomials. I'll show you an example in a second. And if at least one common root lies on the unit circle, then more than one stationary solution may exist, and we will see this in example 3.22 below. Okay, so let's have some examples. I'm not going to do the details, but you will do them yourselves because you are very diligent students. First of all, if I have a look at this polynomial, well, that's the example that I've already done. So I can say that this one is done. Another example would be this polynomial and this polynomial for phi and theta. You use a computer or whatever you want to find the roots, and you see that the roots are this guy and this guy for this one. Of course, there are no roots for this one. The absolute values of these roots are smaller than 1. Sorry, the modulus of these roots are smaller than 1. Therefore, there exists a stationary solution, but it is not causal. There. Another example would be these two guys. Maybe I'll do this one in detail. So example 3.21. And I look at the third bullet point. So we have xt minus 0.05 xt minus 1 minus 0.6 xt minus 2, and you would want that to be equal to zt plus 0.75 zt minus 1. That's the equation that we're working with. Okay, and the polynomial phi of z is therefore this guy. Polynomial theta of z is this guy. If you, well, either you solve by hand or you ask your software to solve for you, you can see that the roots of phi are.
Excuse me.
Yes.
Can you give an example of how to solve this equation with a software? Because I've never used one to solve one of those equations.
So you know how to do them by hand?
Yes, I guess.
Yeah.
I
So
could try.
we have this. So I'll do it once by hand, and then I do it with the software, and
Okay.
you will never do it again by hand in your life. So if we do this, then z is equal to - b. plus ou moins racine carrée de b carré moins 4ac sur 2a. And then we compute. Okay with that?
Yes, that's okay.
Then the other one is even easier. Okay. Now how do we solve this with a software? Well, you could use R. I'm not sure I remember right now the command in R. Sorry, I'm not going to. I'm working on my iPad, so I will. No, I can't really share what I'm doing on my iPad. Yeah, so it's just solve, and then you do what? So to do this, you just write solve, and then what do you have to input? Oh no, that solve is for linear. Does somebody remember the command in R? Nobody? Oh, maybe it's called. It's intensely logical. Maybe it's called find root. So find the roots of a polynomial in R. It's called polyroot. Okay, it's called polyroot of your thing. Wait, I'll share you my screen. It's gonna be easier. Which screen is it? I guess it's this screen. Yeah. So there you see. Are you still there?
Yes.
Okay. So I just typed. I couldn't. I couldn't remember. So I just typed in Google find roots polynomial R. First answer was this. So I guess it's called polyroot. Yeah, good. And then I just have to do it. So here's my R language. And then I want. So what's my polynomial? It's 1. Okay, so I'll do polyroot. I'll do the first one first. So it's 1 0.75. Is that correct? So this I know the answer. Yeah, that looks okay. And then my next one is 1 minus 0.05 minus 0.6, and these are my roots. So here my roots are equal to minus 4/3 and 1.25. So that's 5/4. That's okay for you?
Yes.
Yeah. And also what you can do, I mean, it's better to do it in R because you'll be doing everything in R anyway, or in the same software, but you can also use Mathematica, or you can use Wolfram, or I mean there's many things. So I prefer Wolfram often. It's more it's nicer. So you can also do it with this, and I think it's called solve. Yeah. So this one is a bit more intuitive. So here's another example. I think that should do it. Not sure. Yay! That does the job as well. Okay.
Yes, thank you.
Okay, so I'll share again my. You see my slides again? Yeah. So there we are. So here we see that we have we have a common root. We have that guy and that guy. But that means that our initial equation, this equation here, is in fact simpler than what it looks like, because in fact it's what? It means that theta of z is in fact what? It's 1 plus 0.75 z, that doesn't move, and phi of z is in fact 1 plus 0.75 z times 1 minus 5/4 of z. Does this look okay? I think that's okay. Multiplied by 16. No. Yeah, so I think that's okay, and therefore our equation is in fact can be simplified because you have the same pre-multiplying polynomial here, and the idea is that whatever, sorry, it's not an x, it's here, it's z. The idea is that if you have something that's solution to this equation here, it will also be a solution to this equation here. So at least when you're hand waving, you can eliminate this common factor in your polynomial, and then you simply solve for the remainder. And if you have a solution to this, it will necessarily be a solution to this one as well. Okay with that? So when your polynomials have common roots, well, you just start by getting rid of these common roots, and then you solve whatever remains. And if the conditions are satisfied for what remains, then you will have a stationary and causal solution, and then this will also be a stationary and causal solution of the equation with common roots. So because of that, it means that typically we will not consider common roots in the theory, because the case of common roots is just solved by considering polynomials which don't have a common root, at least common roots which are not on the unit circle. So far so good?
In the equation, the z is then for the backward operator here?
Oh yes, sorry, it's for the backward operator.
And can we remove it like this if it's multiplied by xt and by zt in the other case? I mean,
it's not perfectly obvious, but yes, you can. If you have something which solves the equation where you have removed this part, so if xt solves this, then necessarily it will solve this. Okay. So that covers this example and this example. No, I made a mistake here. It's not 5/4, it's 4/5. Because the solution is 5/4, so it's 4/5. The solution is 5/4, so here it's 4/5. Okay, and the last example, well, I'll put it in orange because I'm not going to do them, but I'll let you read this. I'll let you read this. You ask me questions if you have any. Well, this so the AR1 case we've already done it. It would be interesting to discuss the moving average case. I don't think I did it. That's a bit silly. So if another exercise for you to do is to check what happens in the moving average example, and then yeah. So what I'm going to say here is not very fair. This would be a good example of an exam question. I'm not going to do it in detail because it's too long and it's not really very interesting. But it would be a good example of an exam question because, well, it's got lots of lots of computations that you need to do. But the idea is I probably would never ask this as an exam question because it is a bit boring and it's not very interesting. The idea is to look at what happens in the case of an AR2 process. So instead of having only one order 1 in your AR polynomial, you have order 2. So you have an order 2 here. What happens? Well, it's going to depend on the roots of this second degree polynomial. And well, to cut a long story short, this second degree polynomial will have 2 roots, possibly, and according to the positions of these 2 roots, you will have or you will not have your roots inside or outside the unit disk. And well, all this is just computations where you're trying to understand what's happening. I advise you to try and read this and understand it. And after some rather boring computations, okay, so my kids are back, but they are sick. That's wonderful. I know you don't really care, but my wife works in COVID and we're always a bit stressed. Anyway, to cut a long story short, it depends on the positions of phi1 and phi2, and you can see, well, it's a rather boring exercise, that stationary solutions, if and only if these 3 conditions are satisfied, phi2 has to be less than 1 plus phi1, phi1 has to be less than 1 minus phi2, and phi2 has to be between minus 1 and 1. And does this link work? Yay, it works. Oh, it's already open. So the page seems to have gone wrong, but the illustration still works. So here what you see is an AR2 process. The red dot indicates, forget what it indicates. Yeah, so the region in which you have existence or non-existence of solutions is in fact some kind of triangular region, and here he's just plotting so on the top right you see a simulation of the process with the coefficients which are defined in the top left. And you see that as he's moving around this region, along this triangle that he's drawn, you will have, sometimes you have solutions. Here you have no solution. Here you have a nice stationary solution. Then you get no solution, no stationary solution, and it explodes, and so on. So you see that he has a lovely simulation of the behavior of the solutions, depending on the position of the parameters. And what you see is that in the yellow and green regions you have a nice solution, and otherwise you don't. Sometimes it just explodes, sometimes it's not causal. Okay? But sadly the rest of the text has gone wrong for reasons that I can't explain. Okay. So far so good. I see no questions, but I mean, you'll have to read this up by yourselves, so I'm just giving you an indication, but I mean, this is work that you have to do, or at least you have to convince yourselves that you don't want to do it, and you don't want to do it not because you don't understand it, but because you find it boring. If you don't understand it, then you have to do it. If you understand it and find it boring, then you don't have to do it, if you see what I mean. Okay, now there's something else over which I will go quite quickly, but it's also important, is that obviously in so far, the ZTs were the noise and the XTs are what we saw, and we were constructing XT from the unobserved noise. It would be interesting to see if we can reverse the process, so if we can find an expression of the noise in terms of the observables, because if that is the case, then we are probably in a better situation. An example, if we look at a moving average process of order 1, like this, well, if we have this guy here and this guy here, so this guy has the noise which is IID would mean 0 and variance sigma squared, and this guy has noise which is IID would mean 0 and variance sigma squared theta squared for some theta here. Well, this guy and this guy are zero mean Gaussian with the same covariance. They are indistinguishable in terms of the quantities that we would be interested in, but for some reason we will prefer to use this guy rather than this guy because this guy will be invertible. Well, not even. I mean, depending on the value of the parameter here, we will sometimes prefer to use this guy or to use this guy in terms of in which case we are able to invert the equation and express the ZTs in terms of the XTs. And the condition on the parameters of your polynomial which gives you invertibility are basically the same. In order to be able to inverse, you simply have to have this guy which has so this guy and this guy have no common roots. I use this chic expression that they are co-prime, and in order for the relationship to be invertible, well, simply you have to be allowed to move the theta here to this side here. And if you're allowed to do this, then you're in business to express ZT in terms of the XTs. And when can you do this? Well, if this guy has no roots inside the unit disk. So in terms of invertibility, well, the ARP processes are much nice because this theta polynomial has no roots, so it's always invertible. But in fact, it's trivially invertible as well, because ZT is directly expressed in terms of XTs. So this is easy. And in the moving average case, now this is not just an accident, it will come back again probably today, although maybe not. Maybe I won't go into this today. I'll do it next week. In terms of the moving average process, the invertibility is not easy to see, because in this case it's not easy to relate ZTs to the XTs. In fact, it's the inverse of the AR relationship, because the AR, you had a polynomial in XT equal to ZT, and now we have a polynomial ZT equal to XT. And to have invertibility, well, we need that this polynomial has no roots, so it's in terms of the theta 1 if theta 1 is less or larger than 1. Okay. Now, a lot of work for you. So I'll go over this quite quickly, and then I think I'll stop here. No, I'll go over this last section quickly, and I'll stop here, and then I'll do the detail next week when you'll have read it, because it's I mean it's a lot of computations that you need to be able to do. So of course, one of the objects that we want, I mean the main object that we want to have, is the autocovariance or autocorrelation function of your process. That's the only thing that's of interest, because that's the functional in which we've encoded all the interesting behavior of our process, at least at order 1. So we have the mean, we have the autocovariance. Now we have the ARMA model, we have the polynomials, and let's suppose that everything is going fine. So everything is nice. XT is causal with respect to ZT, so it means that phi has no roots inside the unit disk. These guys have no roots in common, and we have been able to express this guy here. Well then, the mean of the process, we have it. It's just a combination of the psi j's, and the covariance is also just a combination of the psi j's. So these psi j's contain everything we need to know. We also know that this sequence is such that the corresponding series converges absolutely, and in particular, if this is true, well then necessarily psi j goes to 0. Therefore, the coefficients of the zt's in the representation, well, they will always be going to 0. We don't know how, but they will be smaller and smaller and smaller. Now, we know from corollary 3.17. Where is it? We know from corollary 3.17 that the covariance function of our ARMA process is this. So in order to get this covariance function, all we need is to get the psi j's. But now let's come back here and remember, even in this simple case here, no, it's not here. Here. So even in this simple case here, the psi j's were far from obvious because they are computed as the coefficients in the expansion of a complicated polynomial. So even in this case here, the psi j's are rather mysterious. Now, in order to get the covariance nonetheless, well, basically there's 3 ways. And the first way is by brute force. We compute these guys. We compute these psi j's, all of these, this one, and so on. We compute them, and we get the relationship here. Okay, so how do we compute these psi j's? Well, either you use a computer to determine the coefficients of the series expansion, or you think a bit, and we can try and do things a bit by hand. Now, how do we do that? Well, psi of z times phi of z is equal to theta of z. That's the relationship. Well, psi of z is this, phi of z is this, theta of z is this. This must hold for all z. Well, then we simply expand this times this. This gives us a polynomial. Let's have a look. So if I do this multiplication here, I will have psi 0 minus phi 1 psi 0 z minus phi 2 psi 0 z squared minus and so on. Then I will have plus psi 1 z minus psi 1 phi 1 z squared minus psi 1 phi 2 z cubed. Okay, this has to be equal to this guy here. So what's our independent term? Well, we have a 1 here, and we only have one independent term here, which is psi 0. This means that psi 0 has to be equal to 1. Secondly, the terms in z, well, we have this one and we have this one, which has to be equal to this one. This gives us the equation which is here, which allows us to determine psi 1 from phi 0, phi 1, and theta 1. So we get psi 1, which is here. Next term, the next guy is in terms of the square. So that's a square, that's a square. I think that's the only one that will be a square. Oh, no, there's another one. Yeah, so there's going to be another one which will be a square, which has to be equal to theta 2. So we'll get this equation here, which will allow us to get psi 2, and so on, and so on, and so on. You get the idea? Well, you can do this, and you can obtain the coefficients. And this, I mean, I'm not going to do it with you. You have to do it by yourselves. It's a very worthwhile exercise. Get the coefficients of the series expansion of the covariance of an ARMA 1-1 process. I'm not so sure if I didn't make a mistake. I'll check it out. Maybe I'll do this next week. Maybe not. Depends really on how slow I will be in correcting the exercises. So I'm not quite sure that this formula is correct. Maybe there's a mistake. Yeah, you have to check it out. There are exists which allow you to get the general form but I basically couldn't be bothered with giving them to you, so you can go and see page 36 in Appendix B of Nusser, and you'll see how ugly it is. I mean, even for the ARMA 1.1 case, it's actually quite ugly, and it just gets worse and worse as the orders grow. So that's the method number 1 for getting the coefficients of your autocovariance function. Method number 2 is much more elegant. I actually quite like it, and it's something that's going to come back again. So we start from the initial equation, this here. We multiply both sides by xt minus h. So xt minus h here all the way, and xt minus h here all the way. And we take expectations on both sides, so we have this expectation here. So it's just the expectation of the sums. A is equal to this expectation here. So far, okay. Should be at least. Then, this is just the covariances. This guy here. That's the covariance at lag h. That's the covariance at lag h minus 1, and so on. And this is what? Well, xt minus k is a linear combination in terms of the psi j's of the zt minus k minus j's, just by definition. And this is uncorrelated with all the zs's for larger index, and therefore, well, you just compute this and and therefore we know that this here will be equal to this. And then when you just plug it in, this gives us what? It gives us yeah, sorry. Then this gives us that this is equal to 0 if h is too large, and otherwise it's just equal to the sums of the thetas times the psi j's times sigma squared. And therefore we have that this thing here is explicit in terms of the psi j's and theta j's. This thing here is explicit in terms of the covariances. I mean, that's just gamma of h minus phi 1 gamma of h minus 1 minus phi p of gamma of h minus p. And then we have a system of equations which relates gamma h with the psi j's and the thetas and the phi's. And we solve that, and we get the solutions. Again, I'm not doing this for you, you have to do it yourselves. We can use this to compute the autocovariance in an AR2 process. Okay, I'll let you do this. Yeah, I'd forgotten that I put in the exercises. So it's one of the exercises, and you will get these neat expressions. What's important here is that we have computed the autocovariance in general in the R2 case, and what you see is that it's a nice autocovariance which goes to 0. It's not like, so the autocovariance in the moving average case was something and drops to 0. Here it goes to 0 like with an asymptote of some kind. And it's actually quite obvious because you can see that it's simply given by a power of something which goes to 0. And I will conclude today, don't know about you, but I'm a bit tired, by reversing the arguments and saying, well, we know how to compute the ACF of certain ARMA processes. And conversely, let's imagine that we have a process whose ACF is of the form of that of an ARMA process. What does that mean about the process itself? And we have these two properties which will play a role, but I'm not going to prove because the proofs are a bit too complicated, at least for this course. It's that, but they're very important, very, very important. Yeah, So the first proposition is that if you have a stationary process which has mean 0 and whose covariance is equal to 0 for all h larger than a certain q, so that's exactly the same as the covariance of the moving average process. Well, I don't know where it is. It's somewhere before. So if we have a stationary process whose covariance drops after a certain lag and is equal to 0 for all higher orders, well, then it is possible to show that your process is necessarily a moving average process. So that's very important, because it means that if you're looking at your autocovariance of your process and you see it's something and then poof, it drops to 0, well, the only way for this to be the case is that your process be a moving average of order q. So that's quite useful. And secondly, no two ARMA processes will have the same covariance. Well, no, that's trivial. But no two stationary processes will have the same covariance as an ARMA process. In other words, if you have a stationary process which has a certain ACF, if another process has the same ACF, then that process is necessarily ARMA. So that means that within the stationary processes, you can read from the form of the covariance the ARMA structure. Okay, so there's still quite a bit of work for you to do here. I'm obviously available if you want to ask me. And I think it's time to stop. So we're getting out of the hard stuff. We're going back into the nice stuff here now. So should become easier again, the course. Except maybe this section here. And we still have one fundamental concept to define, which we haven't defined yet. It's the partial autocorrelation function, but that will be for next week. I think it's time to stop. Okay, so I'll stop the film.